All right, so now we move on to lesson 3 of Unit A, and that's analysis of graphs with uniform motion. So this is really fundamental for moving forward into lab number 1 because we're going to actually deal with this specific skill on that first lab. And then a couple of the components will translate into lesson 4 and onwards into lab number 2, but we need to understand that this will be really fundamental for our understanding of how we read graphs in terms of this uniform motion approach. Now, let's start off with a bit of key information here. So position time graphs, also known as displacement time graphs, well, these are both vector approaches to graphs. Now, if there's no direction given, then we can say that this is a distance time graph or something that is scalar. But until then, if we're given this position or displacement, we wanted to actually tie these two pieces of terminology together. And so I'm actually just going to use arrows to represent this. Now, what we're going to do is say that position time graphs or displacement time graphs, or even distance time graphs if it's scalar, are relative of saying I'm at a certain position given to a certain time. And now if we want to analyze the slope of these things, well, I'm going to deconstruct these just slightly and then talk about scalar versus vector approach and then what the slope actually means. If we talk about displacement, well, we talked about this in the previous lesson. Displacement is some sort of vector quantity. And so I want to write that in right away, meaning that this has not only direction, but it has some sort of magnitude. So the magnitude plus direction equals some sort of vector. Whereas if we just look at the distance, distance is a scalar value. And scalar meaning it doesn't have any sort of direction, it's purely a how much equation or a how much value. Now, if we talk about the slope of these things, the slope of a displacement time graph is the velocity, because velocity is a speed that includes direction. And then in terms of the scalar approach, when we talk about distance versus time or a distance over time, making the slope of that graph, we're going to get a speed. And we know it's speed because it's the scalar version. It doesn't include any direction, purely the magnitude. Now, something to highlight right away will be this line here that says, if I have a negative slope, it does not mean the object or whatever it is slowing down. It's not to be seen as, oh, this speed is changing or there's some sort of deceleration. That would be the wrong approach to it. You got to always just think about it as a negative means that there's some sort of direction to this, whether it be to the left, whether it be west, whether it be down, whether it be south. We just want to use negative as a convention of representing direction rather than actually talking about slowing down or speeding up, because we wouldn't say positive is speeding up. That would be totally wrong. Now, another line we want to highlight here is that any straight diagonal line on a D versus T graph represents uniform motion. And the reason is because if I have a straight line, what does that technically mean? It means my slope is remaining the same or remaining consistent. And if the slope stays the same, you know there's no change in overall velocity or change in speed, so therefore there shouldn't be any acceleration. Now, if we end up seeing a curved line, that essentially means that the acceleration, it means a change in velocity or a change in speed per any given unit of time. And we know that would mean that any sort of change in speed or velocity, that has to represent there's acceleration, either positive acceleration or something that might be slowing down, which is decelerating. Lastly, we want to highlight the line that says a horizontal line means that the object is not moving. So if I was to kind of put a descriptor graph off to the side here, which I'm just going to do for a second, I'm just going to create a basic graph that is a V versus T graph. So I'm going to have this here, and I'm going to have D. And I should have said distance versus time, or even displacement versus time graph on the side here. So let's go through those three scenarios really quickly here. A negative slope does not mean the object is slowing down. Well, okay, let's do that first one, and we're going to show it in red. So if I have this negative line like this, well, if a negative amount of distance or overall position is being covered over time, that just simply means that the object is moving in the negative direction. So I'm going to put an arrow on the end of this thing, indicating that's the direction that this is heading over time. So there's getting less displacement or less position over time. That means this thing would be having some sort of negative overall velocity, or we could say negative speed. But it wouldn't make sense to say negative speed because remember, speed is just purely magnitude. Okay, now any straight diagonal line on this is uniform motion. And so if I look at that red line, or even if I look at the opposite case, which is a positive slope like this, if you look at this, the slope, no matter where you took it on this given line, you could take any 2 points along the blue line or any 2 points along the red line, you would find that the slope remains the same, meaning that there's no sort of change in overall velocity or change in overall speed, therefore no acceleration. Now, if I saw a curved line, that would simply look like the green one here. And so I'll try to draw it in over as an overlap. Let's say I start at 0, 0, and then I increase in this manner. That would be an example of accelerated motion, because as I'm going to show on the black lines here, if I draw points of tangency, well, clearly the first one, which I'm going to label here, number 1, has a different slope than number 2. So clearly that must be accelerating. Or if it was the opposite way and it started curving down, we would know that the object is decelerating. Lastly, I'm going to show in orange here a horizontal line. And if I have a horizontal line, this simply means that the object is not moving, because as you can see here, as time is progressing, am I changing in vertical height, aka am I changing in position over time? Definitely not. I'm remaining at that same distance on the y-axis over time, thus I must not be moving. So if you want to draw in a little visual for yourself to represent each of these, you can, and just kind of walk through yourself through that logic there. All right, now considering graph number 1 here, what we're going to do is we're going to figure out the slopes in the following 3 places. First of all here, second of all in the flat horizontal line here, and then lastly in this section here. Now to do this, here's what we're going to do. We're going to put dots in the following 4 positions. Now, alongside of that, I'm going to make sure I label the coordinates. So I'm going to do 0, 0. I'm going to go up here and say this is at a position of 15 on the time axis, or 15 seconds, and 12 in terms of the position, or positive 12. In terms of the other point, it looks like this one is going to be at 25 seconds, so I'm going to put 25 for x, and then for y, it's still at the same vertical height, positive 12. Lastly, I have something that's at 35 for the seconds, and 0 in terms of the position. Now remember, if they say position, that means that this thing has some sort of vector quantity, because it's positives or negatives. Position is the same as displacement. Rather than saying, if I just simply say distance, you know that that is a scalar value, meaning there's no positives or negatives. It's just simply how much. Okay, now the point of this is we want to calculate the velocities during these 3 intervals. That's what this bubble says here. So what we're going to do is we're going to calculate the slopes at those 3 following regions. So starting off with number 1, we're going to calculate the slope by doing y2 minus y1, x2 minus x1. And so in the numerator, I'm going to get 12 minus 0 over 15 minus 0. Now, as an answer, when I simplify this, I should get 4 over 5, which then would give me an answer of, if I write it slightly below here, positive 0.8 meters per second. Now you're probably like, why do I include a positive in front? Not only is it a positive slope, it's a vector quantity. This is a velocity. Position over time means we have some sort of velocity, so we need to include sign. Now, without even doing a calculation, horizontal lines from Math 10C always gave us something of 0 slope. So what is it? 0, but not only 0, 0 meters per second, and that represents our second slope. Our third slope, we're going to have to use the calculation we just used on that first piece. I'm going to say m is equal to, well, y2 is 0 minus 12, which is y1, divided by, we have 35, which is x2, minus 25, which is x1. Now, this is going to simplify to the following. M is equal to, we're going to get negative 12 over 10. And then if I write in the answer here, I'm going to get the slope is equal to negative 1.2. There we go. And not only 1.2, but 1.2 meters per second. Now, the sign is incredibly important. Why? Well, it's a negative slope, so I should expect to see some sort of negative overall velocity. And again, these negatives and positives don't indicate anything about, oh, speeding up or slowing down. It's not like it's saying it's speeding up here and then all of a sudden slowing down. What we want to consider and say is, this is moving in a positive direction, and then this is just the opposite direction, negative. And realistically, we could play with our axes a ton, and we could flip these around and say, negative is in the right direction, positive is in the left direction. But according to our course, remember, when we drew out our Cartesian plane, we said positive was up and to the right, and negative was down and to the left. And so we're just going to keep following that notation throughout the semester just to create a really uniform approach. Now, they ask us a specific question here. They say, is the instantaneous velocity during any given time interval the same as the average velocity during that same interval? Now, to break that apart, here's what we would look at. If I consider the slope at this given point, would it be the same as anywhere else on this line or this diagonal line? And the answer is yes, because if this is a slope that does not change, That means that the overall slope from the entire line, or how I should phrase this is, if we go back to 10C, we looked at this and we said the slope, no matter where you looked on these lines, was the same. It only changed if there was any sort of curvature in the line. But as long as the line remains straight, or diagonal in this case, we saw this and we said, well, the slope remains the same, hence the velocity remains the same along the whole thing. So is the instantaneous velocity the same as the entire interval? Yes, because you would get the same slope, aka the same velocity. And so what we want to say is yes. Okay. Now, as we move on to velocity versus time graphs, remember, this is where we shuffle in and we say, okay, going forward into lesson 4 and lab number 2, this is going to be a critical piece of knowledge to have here. But again, we're just going to break it apart in terms of definition here. So again, if no direction is given, we just know it as a speed versus time graph. But for the most part, we're going to look at velocity time graphs for pretty much the majority of problems. But if we do see speed versus time, just know it's the scalar approach or the non-directional approach. So as I underline these again, just like we did in the past part, velocity is a vector quantity. And so I'm going to write that in here. This is a vector. And then I'm going to put an arrow over to our speed indicating a scalar value. Okay, now if I was to calculate the slope of a velocity time graph or a speed versus time graph, I want you to realize one thing here. Well, suppose I do that. If I take v over t, that's like saying if I plug in the units, meters per second divided by seconds. Now, what would happen algebraically, and if you work this out for yourself, you're going to get where the seconds both go to the denominator and square. And if they both go to the denominator, now we get meters per second squared as the fraction of this, or as the ratio of this, or more importantly, as the slope of this. And if we get the slope of a v over t graph, what we end up getting is acceleration. Or more specifically, we get acceleration when we take velocity and divide it by time. Now, if we divide speed by time, all we get is the magnitude of the acceleration. Because remember, it's not directional. So all we're going to get of this is the magnitude of acceleration. Whereas acceleration, we know, is some sort of vector quantity. And when we get a vector quantity, of course, it has some sort of sign here. And let me clean this up here just to make sure we get the full thing in here. Acceleration. There we go. So just the magnitude when we talk about scalar. Now, something to just like really point out here, just like we did before, if I have a straight line on this v versus t graph, that means that I have some sort of uniform motion or no acceleration. And what more particularly, it's a straight horizontal line. It's not having any sort of slope. It's going to be a zero slope. This means we have uniform motion because the velocity is not changing, or more importantly, the speed is not changing. You could use it interchangeably. Now, in terms of a straight diagonal line on a v versus t graph, this just means that there is non-uniform motion, and we're going to see lots more of this in lesson 4. Just like I said, when we deal with our first lab, we don't want to get super obsessed with the material around acceleration, but when we move on from lesson 3 to 4, we're going to see lots more of this, so just be aware that you're going to see that. Lastly, this last note here, in this course, you'll not see a curve v versus t. The reason is because when we have curved v versus t graphs or curved velocity versus time graphs, it actually creates a lot of confusion because you need calculus skills in order to figure out not only areas to get certain properties of these, but on top of that, you need to use calculus to find the instantaneous velocities at any given moment. And so we don't really want to do that. Once you get to calculus, maybe you can look back at this and then be like, oh, okay, that's actually a lot easier than I think. But at that point, you'll be brilliant. You'll be geniuses. You'll be moved on to bigger and better problems, I should say. So don't be too consumed about that. Just know that we won't see any curved v versus t. The most we're going to see is either a diagonal line or a horizontal line. Okay, now let's create the graph of a v versus t graph from a distance or displacement versus time graph like we did. Well, on the previous slide, what we did is we took the information that was given to us in the position versus time graph, and now what we're going to do is just record it down below here just to use it and then translate it into a v over t graph. So in the 0 to 15 second interval, we got a positive 0.8 meters per second. In the middle one, when it was a horizontal line, we got 0 meters per second. There was no slope. And then lastly, we got negative 1.2 meters per second. Now, what we're going to do is we're going to take these time intervals and the velocity during those time intervals and plot them on a graph that is a v over t graph. Okay, so let's take this graph and do that. First of all, we had in our first velocity 0.8. So what I'm going to do is I'm just going to go up to 0.8 and draw a horizontal line for 15 seconds. 0.8 to 15. There we go. Now, that represents a velocity that is not changing during a given interval, aka there's no acceleration. We flip back here and we go from positive 0.8 meters per second to 15 to 25 seconds, aka 10-second window at 0 meters per second. So what I'm going to do is I'm going to draw my line straight down, connect it, and then draw it over to 25 and stop. Okay, that's my 0 meters per second, meaning what's actually happening? The object's not moving. If they're not moving at any sort of speed or velocity, then we know that this thing is just at rest. Now we're going to go into our last interval, negative 1.2 from 25 seconds to 35 seconds, aka another 10 seconds pass at this new velocity. So we're going to draw down. I'm going to go all the way down to 1.2, which I believe to be here. And then I'm going to go over for 10 seconds, which puts us to 35. And there's our end position. Now, one thing I want you to point out right away, or one thing I want you to be analyzing and thinking about is, would it ever make sense in real life to start at a certain velocity, all of a sudden go to 0, and then all of a sudden go to a new velocity that's in the opposite direction? No, in fact, this is pretty unrealistic. This direct vertical drop on both of these graphs, often you're not just going to go from one velocity to another instantaneously. That's called time travel. And so realistically, this doesn't have much applicability. But what we could do is just generalize the problem and say, hey, maybe the person is walking a little bit away from their house. They leave their house to go to the mailbox. On the way to the mailbox, they go there at 0.8 meters per second. Once they reach the mailbox, they then are there for 10 seconds at rest. Then they leave to go back to their house and take 10 seconds at this new, quicker speed in order to return. So you could think about the problem in that way. Like, just use your imagination. Whatever way would say you're moving in one direction, and then on the return trip, when you have a negative velocity, aka you're going the other direction, and then you can invent something about the middle where they're not moving at all and they're just at rest, what might be happening there, and then ignore this instantaneous change in velocity because it's not super realistic for us. Okay, now, if we want to figure out, and I want to make sure I didn't skip a slide here, perfect. When we want to find the distance and displacement from V versus T graphs or V over T graphs, first of all, we can figure it out using one of our simple formulas that we derived in lesson 1 and 2, and that is the V equals D over T. If I multiply the T up to the numerator, aka, here's what I'm going to do. I'm going to take our formula given and multiply up T. Well, that gives me the formula in the second line, which is D equals V times T. And when I multiply these two things together, I get the distance or displacement, depending on which type of information I'm given. So let's do an example of this on the next slide. Suppose I want to figure out what the distance and the displacement of this are. Well, what I would like you to do is I want you to sketch out a boundary line right here for the top graph. And then what I want you to do is I want you to go below and sketch out a rectangle for this lower section. Now, what did we do? What we did is we created a boundary between the velocity line and the 0 line, or what we can typically call our reference point, or our reference velocity, if you want to call it that. So I'm just going to call 0 the reference velocity, and then all of our velocities, we're going to compare in relation to that line. And when we solve this for distance and displacement, we're calculating the areas that are contained within the velocity line and the 0 reference line. Now let's do a little bit of labeling here. On the y, we have positive 5 meters per second. On the x-axis, we have, or on the, I should say the length of this, we have 15 seconds. Now let's do the same labeling for the other one. I have from 0 down to 10, so I'm going to call this 10 meters per second. And I'll just write in the negative there just to indicate that it is in the downwards direction or in the opposite direction. And then from 15 to 35, we know this is 20 seconds. Now let's calculate the distance. D1 is going to be equal to V1 times T1. So this is going to be equal to, I take the 5 meters per second. Remember, this is just scalar values because we're just talking about distance, times 15 seconds. This is going to give me 75 meters. Okay, now I want to do the same thing below. D2 is equal to V2 times T2. This is equal to, again, no signs here because we're just talking about scalar amounts, times 20 seconds. This is going to give me 200 meters. And let's see if I can squeeze it in here. I don't know if I can. Oh, it's close. Yeah, okay, perfect. We're going to settle with that. Now, off to the side here, what I'm going to say is, therefore, if I add these two things together, d1 plus d2, aka I get the change in the overall distance, this is going to be the sum of those two parts. What are the sums? 75 plus the 200 meters. When you add those two things together, you get a total distance or a total change in distance of 275 meters. And so we'll highlight that component here to indicate we got one of our answers. Excellent. Now, all we're going to do is to change our approach just very slightly in order to get the displacement, we're just going to account for the vector quantity. So I'm going to go displacement 1 is equal to velocity 1 times t, which is equal to positive 5 meters per second. You can see I added a sign times 15 seconds is equal to positive 75. To none of our surprise, all we've done in the end is we just added a sign representing direction. So it is positive 75 meters in the one direction. Now, for the other one, what we're going to do is we're going to say displacement number 2 is equal to velocity 2 instead of speed 2 times t2. This is going to be equal to negative 10 meters per second multiplied by the 20 seconds. And rather than squeezing it off to the side there, actually, maybe I can here, we're going to get negative 200 meters. There we go. I know it's a little bit squishy on that right-hand side, but that'll be okay. Now, in order to get displacement, therefore, displacement number 1 plus displacement number 2 is equal to the change in overall displacement, or the net change in the position of this object. When we add these two things together, I'm going to put positive 75 with negative 200. When I add those two things together, I end up getting negative 125. And so if you were to summarize this solution, what you would say about this is you would say, well, in total, this person on this journey that they take, they end up traveling 275 meters. But from where they start to where they end up negative 125 meters, and we could refer that to as negative 125 meters south. We could say that they ended up west or left, but it's too hard to determine from this because they didn't tell us anything about northeast, southwest. So we're just going to assume that that means that they are in one of the directions, either to their left or right, negative 125 from where they start to where they end overall. Now, the one thing I'm going to note about this problem is that this is pretty straightforward. We just take those areas of the rectangles, we create these boundary lines, and we then add them together. That will give us distance displacements. What we need to be really careful about is in the future, we may get triangles. So we may get something that looks like the following. Here's one component attached to a square. We may have to add the area of this one and the area of this one together. So you might be able to get different shapes. What does that technically mean? If you create a diagonal line representing a diagonal velocity like this, that means there's acceleration. And so if I drew this, that would mean that there's an overall acceleration in the one component and then no acceleration in the other component. Don't worry, we'll talk way more about this in lesson 4. But for now, when we're just talking about uniform motion, just know this is a uniform graph approach. And this is what they would look like if they ever talked about uniform. All right, here's where I want you to get your homework, because this is really important to get practice on, is getting all these graphs done and playing around with these and being like, can I get the different speeds? Can I get different times? Can I get different distances and displacements? And can I piece this all together and really put it all on a graph? Because when you go on to lab 1, you're going to need to have these skills mastered by the time you get to that.